But now we're going to go see the original solar telescope on the mountain, which was set up in 1904. And basically the queen of the snow is Patricia, which will tell you all about the science. She really was instrumental in making the snow available once again to be seen on our tour. Part of the tour is open to everybody.
My name is Patricia, and you are in the Snow Solar Telescope. It is called the Snow because a woman named Helen Snow paid for it. 150 foot, but this is the snow she wanted to honor her father. Founder of Mount Wilson, George Ellery Hale. This telescope was originally at his first commercial observatory in Wisconsin called Yerkes. You can imagine Yerkes was not good for solar or anything, so he was out of there. He knew about Mount Wilson as a site as early as 1889. He was an undergrad at MIT studying physics, but he was working at the Harvard Observatory. So he was aware Harvard had a small telescope out here that winter, and they discovered immediately the viewing conditions, which astronomers call the seeing, was phenomenal. Two reasons true then, one today. We're at 5,700 feet, we're above the inversion layer, the air is stable, and back then little to no light pollution. Prior to Mount Wilson, observatories were strictly for observational astronomy. They were cataloging, they knew phases and cycles, they knew where stuff was, but they didn't know what anything was made of, the physics of it. Hale founded Mount Wilson as the first observatory dedicated to the field of astrophysics, which at the turn of the 20th century was new and people were not quite sure. To do astrophysics, the main tool you need is called a spectrograph, and the key component in the spectrograph is a piece of scored metal called a diffraction grating. It has parallel lines scored really close together, and they have an angle group. So the slit to the spectrograph is stationary, the light comes in vertically, but as you tilt that grating, your angle of reflection changes and you get different wavelengths. So because Hale outfitted all 5 telescopes with spectrographs, cameras from unexposed century were made at Mount Wilson. So it's a really significant observatory for multiple reasons. So it's all about spectroscopy. We know we just see the middle of the electromagnetic spectrum. The spectrograph opens up all that info on both ends. This is what spectroscopy does. You are in a cutting edge telescope from the early 1900s. This scope is 120 years old. Now, once you start to break light up into wavelengths, using that good old spectrograph, you're going to be looking at a different version of the periodic table. So this is the periodic table of spectra. Each element has its own light fingerprint. And from these emission lines, there's also absorption lines that you'll see in the telescope. You can determine movement, temperature, composition, density, mass, all kinds of things. So this was a really important tool, still is. And we have 3 types of spectra. You'll see 2 here today. The first type is called just a regular old continuous spectrum. And I have a small piece of diffraction grating. There's my good one. Yeah, I know, it's a crowd pleaser. So that, it's the same thing you see in a rainbow when, you know, the rain bends the light. So that's a continuous spectrum. The type you'll see here, we call this a stage, will have black, or they read more as dark gray lines called absorption lines. Absorption lines are formed when the light source goes through a cool gas cloud. In the case of the sun, the outer layer of the sun is the coolest layer. So as that light exits that outer coolest layer, the photons are absorbing energy and they're jumping to a higher energy level in the atom. For the emission lines, it's just the opposite. The light goes through a warm gas cloud and it loses energy and therefore drops to a lower level. Kirchhoff was a famous German physicist, and science is all about laws. So this is his law. You can see the emissions moving to a lower level and the absorption's higher. We know the sun and all stars are made mostly of hydrogen and helium, and that's in their core. That's where nuclear fusion occurs. Once the star consumes all the hydrogen and helium, it just kicks out and grabs whatever it can find. When there's no more fuel, the star begins to die. And different stars die differently, but eventually, all dying stars will be surrounded by a cloud of gas and dust called a nebula. Inside a nebula is where new stars form. So stars have a life cycle. Different stars have different spectra. And this is what the spectrograph opens up. So I know you just saw sunspots. Hale discovered with this telescope and the spectroheliograph, which is just an above ground spectrograph, if you will, that sunspots are about 4,000 degrees Fahrenheit cooler than the areas around them. He knew they occurred because of magnetic fields. He could not prove it in the snow, so he just built a 60-foot and proved that. Those two basic discoveries about sunspots opened up the eyes of all those observational astronomers, and everyone realized, okay, spectroscopy, astrophysics, this is how we will literally open up the secrets of the cosmos, and that's what happened. If you look at a sunspot in white light, and we remember that every absorption line and every emission line represents just a single element, we can isolate the iron absorption lines in a sunspot, and we'll see what's called the Zeeman effect. You'll see a bulge and probably a split. Tells you that there's a magnetic field, and it'll tell you what the strength is. And Steve does that in 150 foot. We can use a Doppler shift to tell us about movement, but even better, we can use her formula. Henrietta Swan Leavitt was one of the Harvard computers. Her job was to analyze the glass photographic plates made in the telescopes. She discovered a type of star called a Cepheid variable. They have a cycle of getting brighter and dimmer. From that information, she came up with a mathematical formula to measure distance. Suddenly, they could measure millions and billions of light years, not just hundreds of thousands. She was an early solar astronomer, did work on site here with 150 foot in 1925, and that was unusual. Not many women scientists worked up here. She proved in her dissertation that all stars are made mostly of hydrogen and helium. So, the way the telescope works, before you come to look at the spectrum, stand back here and look through the opening. You'll see two mirrors. They're called a coelostat. The bottom mirror is tracking the top relative to the rotation of the Earth by means of a big flywheel, a cable, and a weight. It's a clock drive. So you catch the sun in the bottom mirror, shine it to the top. Top sends it down behind us to the primary, which has a slight concave curve. The primary sends the beam of light up to the tilting mirror, and then the tilting mirror sends it through the slit, which is the entrance to the spectrograph. The light goes down 18 feet. It passes through a lens, which focuses it on a much bigger, nicer piece of diffraction grating and much older. Breaks it up, back through the lens to this piece of glass where you'll see part of the solar spectrum. Now, this telescope runs on DC power. The DC motors are engaged by the DC relays behind that yellow grate. So this is the sound of a 120-year-old DC relay moving a 120-year-old DC motor. All right, so there you go. All right, so check it out from the back so you can see how it's set up, and then come and look at the solar spectrum. And happy Mother's Day to any mothers here.
Thank you.